in 2008, he was at Grasp Laboratory, and he received his other degrees from the University of Athens. Since then, he's done a lot of activities, as you probably know. One of the things I remember is during his time at the University of Arizona, when I was at my time at University of Arizona and his time at Arizona State University. We will meet, and he was there at the computer science and computer engineering department. He got tenure there, which is a great feat, and then he moved into his current position. He was also a postdoctoral researcher at NEC Laboratory America in the System Analysis and Verification Group. As I mentioned, he's been doing a lot of great work. He was recognized with NSF Career Award and the Arizona State University SIIDSE Best Researcher Junior Faculty Award. I believe that comes from the School of Engineering. And then he's also been doing a lot of great teaching and received a number of awards, including the 2008 Frank Enger Memorial ACM Student Award. And he was also a co-chair for the HSCC that was at a CPS or previous to the CPS IoT week. Was that the first year of the CPS IoT week or right before that?
Oh, I think it was a couple of years after it had started being CPS week. Yeah.
I don't remember. That was 2016. That was in Vienna, is that correct?
Yeah, Vienna. Wow, you have good memory.
I remember. That was a beautiful place. Okay, well, you have anything else to say? Georgios, the floor is yours.
Yeah, thank you for the introduction. Thank you for inviting me. Let's make this kind of informal. Feel free to stop me at any time, ask questions. It will be nice to have a lively discussion. Let me start by the usual disclaimer that even though I'm presenting here as a researcher from Toyota, I don't necessarily present the official position of Toyota. I'm kind of presenting my own opinion as an expert subject matter. All right. So nevertheless, I'm going to give you a brief introduction of Toyota Motor North America and where we are located, just to give you a little bit a sense of our organization, because it's not typically that you hear about the organization. Our organization, I mean, everybody knows Toyota vehicles, but nevertheless, it's typically not obvious how such a huge organization works. We are actually part of Toyota Motor North America, which is primarily responsible for designing, manufacturing vehicles for North America market, but they also have other markets and kind of work on other projects as well. That's the main function. Our unit is called Toyota Research Institute of North America, is within the Toyota Motor North America in the United States. And we have tasked to do future challenges research. Typically, future means 20 to 30 years out. Within this unit, within this institute, there are three subdivisions, three departments: materials, electronics, and what is called future mobility. And within that, we have our own cyber-physical systems group, where these are the members. We kind of do collaboratively our work. Now, Toyota is very well known for making cars. And we are becoming kind of a mobility company, generalizing beyond just making cars. And it may be instructive, not instructive, kind of motivational to see one of these promotional videos about the general concept of mobility. This can be viewed as a mobility, moving people, goods, information. And this is public information, and you can find also the YouTube. This is a presentation actually given by the CEO of Woven City in a recent event in France. So you can view the whole introduction there. I just want to give you a few excerpts of the vision of future smart cities that are being developed by Toyota. I have removed the sound. Can you see the video well?
Yes.
Okay, great. And if you cannot, you can please watch the video, YouTube, the link here. It gives more information. So here you can see there are individualized mobility options. The seat is being kind of a woven fabric. This is being built now. This is the inspirational design. It's actually being built in Japan. You can see these mobility systems that potentially they will be autonomous, individual mobility options. These are actually design systems. The house are going to have robots assisting and so on. Later on, you'll see also packages being flown by drones, air mobility, things of that nature. You can think that the underground of the city is going to be providing facilities for delivering products, fully automated with robots, delivering things to your house. So that's kind of the inspiration here. And I think towards the end of the video, it shows what is the construction stage. I've just reduced the video here for giving you a quick overview. So that's kind of the inspiration, like smart cities, fully integrated, automated. And there are also products that are being developed currently, such as these hospital robots. This is a system being deployed in the Toyota hospital in Toyota City. These robots are moving around, delivering medicine, picking up specimens. It's fully automated system. It does the logistics. They can go into elevators. They can move around among people. Here it's going to exchange some packages. Then this is the pharmacy. They pick up these kind of containers that are stacked by the pharmacists. They move them around in the hospital so that they can deliver supplies to the hospital personnel. And of course, they move in the corridors among humans. Very kind of exciting project. It's very interesting to see this in person in the hospital. The hospital is also fantastic. It's kind of brand new. It's very futuristic. We don't work on these problems per se. We are kind of inspired by smart city, hospital applications. We view these as our inspiration so that we can think the next type of problems that may arise or what might be possible. But we typically would like to think beyond what is being developed currently. And our colleagues in Japan who developed this product or this prototype have also published this nice article here describing their challenges. Some of the challenges you can imagine are about human-robot interaction. Others have to do with event detection and scene understanding, simulation-based testing and verification, and how you close the sim-to-real gap. What you see here on the left side is the real thing, and on the right side is the simulation. So if you look this from far away, you cannot really tell what's the difference. But nevertheless, this is a nice article. I can share that later on a PDF of the slides. You can just read the article yourselves. So within that context, and thinking about the future mobility problems and opportunities, our group's goal is to do risk-aware autonomous systems where we can provide mathematical guarantees on functionality, performance, under uncertainty. And we have three primary agendas these days. First of all is, as always, requirements, verification, validation, testing, and certification. And moving now from the closed-loop cyber-physical systems, where we know very well the parameters for which we are designing the system, towards these open world environments where anything can happen at any time. The other topics we're working on is potentially seemingly diverging a little bit from number one. Another topic is planning and control of heterogeneous multi-agent systems and human-robot interaction. Nevertheless, we view all of these as the same class of problems. Here we design the control potential in the planning stack, whereas here we try to analyze. But for all of these different themes, the goal is to do risk-aware verification, computation, and so on. Now, within the last couple of years I joined the group, we have now made substantial progress towards our goals. We work on formal specifications, as I mentioned. We have task assignment and path planning work. We have work on learning workflows. Here, the idea is that you can observe what's happening and you would like to optimize, integrate more automation in the processes, augment human workers' productivity, and so on. Environmental abstractions. We do local planning, communication and motion planning. Typically here we mean planning with respect to humans. Communication planning for humans, not robot to robot, but rather robot to human and the other way around. Low-level risk-aware control. We may have discussed with your group before about this line of work, for example, control barrier functions, risk-aware control barrier functions. Perception and predictions. And these days, as fashionable, all these things will have some neural network in there. Teaming, monitoring, anomaly detection, which I'm not going to discuss today. Natural language as an input to these systems. And since all these are too much for just a small 4-people group, we also collaborate with many institutions, and the bulk of our work is through collaborations. And of course, everything falls under our umbrella of testing, assurance, digital twins, and all these things that help us assure this type of systems. All right, so what I'm going to talk about today is how do we start from formal specifications and we can potentially design controllers that have neural networks and how we can potentially verify these systems. And I'm always trying to promote formal requirements, so I'll do the same here as well, even though I'm sure you are kind of supporting or you're part of the believers of formal requirements. First of all, why formal logic? We can ambiguously define the operational domain, design domain for a system, which also means we can start reasoning about priorities, minimal violations, and so on. We can automatically analyze the requirements for inconsistencies, and we view this as kind of very important because many times designs can fail due to inconsistencies. We can assist in automated synthesis and formal proofs, which is the topic of today's presentation. And we can guide the process of automatic test case generation and can utilize in runtime fault detection. So all these are kind of the benefits you get by formalizing your functional requirements. So this is kind of the focus for today's presentation. And trying to be a little bit more concrete, imagine that we have a bunch of requirements. Then we'd like to design a neural network controller such that when you compose it with the system now satisfies these requirements. And this is what I'm going to present today is largely collaborative work with USC and University of Nebraska-Lincoln, and I'll give you more details later on. So just to kind of concretize a little bit things, let's think of a simple example. We have an ego car, a lead vehicle, and we have a requirement if the lead vehicle in your lane has velocity greater than 10 kilometers per hour, and the distance from the lead vehicle is at least d meters and at most d capital M meters, then the ego can always maintain a safe distance in the next 3 seconds. So formalized, the requirement would be something like that. So we use the operator always to combine, to create conditional requirements. So if this condition holds, then this should hold for the next 3 seconds. You can relax this by assuming that something should happen in the future if this condition is violated, and so on. This is kind of to show the inspiration behind the work. And there's a lot of work among this, one of my earlier papers, on trying to formalize existing driving rules for within temporal logic, which can then be used for testing, monitoring, and also control synthesis. So in this one of the first papers, we formalized the responsibility sensitive safety rules developed by Intel using temporal logic, and we use them for monitoring, for example. There are other works formalizing interstate traffic rules, specifying traffic laws. I think this was especially formalizing the traffic laws in China and Singapore, I believe, if I remember correctly. Temporal logic formalization of the ISO 34502 critical scenarios. In general, there's a lot of work being developed right now where all these traffic laws are formalized and can give us a wealth of formalized requirements for both assurance and also potentially design. All right, I'm going to not say too many things about neural networks. I'll assume that a lot of the basics of neural networks are known. For example, backpropagation, what is the structure of neural networks. And I'll say a few more words on temporal logics, historical primarily, to give a context how we start using them for neural network synthesis, and also to highlight some differences. If this is known, since it's kind of an informal discussion or a formal presentation, please let me know and can move a little bit faster through that. Temporal logics were introduced in the early days as a way to formalize natural language requirements and remove ambiguity and be able to algorithmically reason and do proofs about computer systems. We start by using the traditional propositional logic, and we extend it with temporal operators. And here I'll introduce all kinds of variants of notation because the slides are coming from different versions and I might be using different notations throughout. So please bear with me. So here G stands for globally, and this means globally from time 0 to infinity, the atomic proposition P1 should hold. This can also be represented as a box, the operator G, or in natural language, you can read it as always. So always require P to happen, P1 to happen. So if you have a state sequence or an atomic preposition observation sequence, you'll always observe that the preposition P1 is going to be true throughout. When we say eventually, between time 1 and 3, P1 must happen. Then we put a bound and we require that P1 will happen eventually. So here I've forgotten to put the bound. So F here stands for in the future, diamond, eventually P1. So P1 happens here. We see the timestamp for P1, which is at time point 1.1. This fits within this bound. So we say that this trace here satisfies this requirement. When we are operating over discrete time, we can also define next time operator. So if we are here now, we require that at the next time P1 will happen. And until operator with time bounds, some time bounds says that P1 should be true until P2 becomes true within this time interval. And you can see here we have this discrete sequence. We have P1, P1, P1. P2 happens. It happens at time 1.1, which is within this interval. So therefore, we say that this behavior satisfies this requirement. And you can start composing these arbitrarily to create more complex requirements. You can do this also in continuous time. Oded Mahler and Diane Nikovich back in 2004 introduced signal temporal logic as a reasoning language over continuous time signals. And therefore, there you could introduce thresholds give a Boolean interpretation to this threshold. So if you have this signal, you have this threshold, you can create a Boolean continuous time signal. And then you can write properties such as eventually between time 2.4 and 3.2, X has to be greater than A. So this is true in this interval. So therefore this requirement is satisfied over this trace. And you can do more complicated requirements. You can say, for example, always in this interval, we have not X greater than A. So this does not hold here because we have true, false, true, right? You can do until and so on. But now you're operating over continuous time Boolean signals. Now, one side comment here that I would like to highlight is that the connection between the continuous time MTL and STL is somewhat trivial. You can have an atomic proposition being mapped to this predicate, and therefore there is an immediate one-to-one relationship between back and forth between MTL and STL. So from my perspective, typically these two are fully equivalent for all purposes, at least theoretical. Just as a side comment here. And long time back in the early 2000s, me and George Papas were thinking how we can use these, how we can give a quantitative interpretation of satisfaction for cyber-physical systems, because by just saying true, false, it's not always giving you enough insight what's happening with cyber-physical systems. So if you write a requirement such as always, if a signal drops below -10, then eventually within some time, the signal should be above 10. So here, this is an example. You drop below -10, then you go above 10, below, above. So both this red signal S2 and then S1 satisfy the same requirement, but they're qualitatively different, right? S1 should tolerate more noise than S2. So how do we differentiate between these two signals? We came up with the notion of robustness. So if you want to say, for instance, eventually the signal should be within a circle, then given a signal, given a circle, we can compute the largest depth that this signal falls within the circle, and this now can become a robustness value. And therefore, we can define a neighborhood around that signal such that we know that any other signal that remains within this neighborhood also satisfies the requirement. So that gives you kind of a natural interpretation of robustness, especially in terms of tolerating noise. You know that if you perturb this signal with up to magnitude here in the blue trajectory, then you'll still satisfy the requirement. And that also extends naturally to falsification or not satisfaction. So if you're outside, then you can define a neighborhood around here that says, if I move up to that much, I will still not satisfy the same requirement. And this is done by computing distances. So the interpretation of the predicates, of the predicate functions or the atomic propositions in MTL that map to predicates is given a depth or distance. So if you're outside the desired set, the goal set, then your local evaluation is a negative of your distance. And if you're inside the set, meaning you satisfy the requirement, then your interpretation is your depth, how deep you are inside the set, and you can now define a ball around this point. And then the composition of the Boolean operators simply becomes min and max. So here, when we have this junction, it becomes maximum operator. If we use a lattice notation, this is now the supremum. If we use a total order, let's say if we give real value interpretation, then this just becomes maximum. The next operator needs to satisfy some constraints. It's not very important, but the until operator becomes a minimum over your observed traces and a maximum over all of the choices. So it's a composition of maximum and minimum operators. And if we use these semantics here and we are given a trajectory, then we can get a robust interpretation. So here we can say that S1 has value 5, and the red one here has value 0.5. And this is the perturbed bounds that we can tolerate. And we can formalize that over both continuous valued signals and also hybrid spaces in case we have hybrid dynamical systems. So I'll skip that. Now, a word of caution. Our original definition was based on distances. So you define a set where you would like to be at, and you're saying, okay, how far I am from getting into that set. And that's what gives you this nice robustness interpretation. Later on, Alex Donze with Odette Mahler, they simplified a little bit the definition, and they gave in the semantics only comparisons between X and a constant, between the variables and constants. And with this type of atomic propositions, predicates, the two notions coincide fully because distances become just also here X minus C, for instance, right? So that will be the equivalent of distance. But later on, people start generalizing that, and they said, and they start allowing arbitrary functions. But when you allow arbitrary functions, then you lose the guarantees provided by computing distances. And therefore, when you say something simple like what is the robustness of this trajectory with respect to the formula that says always you should be below 1, so this threshold 1, if you remain within this fragment where you just compare variables and constants, then you can compute indeed the true robustness, which is 0.5, and therefore you have a due. But if you consider some arbitrary function that represents exactly the same set, so for example, 4x less than 4, right, which is exactly the same as this one, and you try now to use the simplified semantics here to compute the robustness, you will get as a robustness neighborhood 2, which of course is not a robustness anymore. So this is not a robustness notion, but there is a benefit here. We at least preserve the sign of robustness, which means if this is positive, then the requirement is correct. And also, if this function is differentiable, then we can utilize this in neural network training, right? So that's still useful, but nevertheless, I would like to highlight that it doesn't define a robustness neighborhood. May be important in some contexts, but not always, right? So again, very important. If you need robustness, you'll have to use distances. If you just want to have some quantitative version and preserve differentiability of the formulas, then you can relax the semantics and allow for just some arbitrary F value, not compute distances. All right, so a very quick, I guess maybe not so quick, but hopefully I highlighted some pitfalls here. And now I would like to use this robustness notion to train neural networks. Are there any questions so far?
Any questions, anybody?
All right, so let me proceed. So here's the setup. We have a neural network which computes our control input. We would like to compose this with, of course, our system plant. So we have our plant, we have some observation. It goes to the neural network and we compute the input. And our goal is to find weights W so that the closed loop system satisfies some specification in temporal logic. So how do we formulate that problem? Some time ago with my former student Sakiba, now she's at Motional. I was back then at ASU, but actually this was for a project for Toyota, so I can mention that here as well. So our goal here is to compute the weights for the neural network such that the minimum robustness that we are defining for our neural network is maximized, right? So our goal again is to find the minimum robustness over a specific set of weights and maximize the minimum robustness. So that will be kind of a robust version of a neural network that would satisfy a temporal logic requirement. So here what you see is the robustness, the temporal logic requirements, and we our representation assumes that the trajectory generated by a neural network depends on the weights of the neural network. Okay. So we have a couple of issues. If we use the original robustness interpretation, we have, first of all, non-differentiable cost loss function for our neural network. And second, we have here an infinite operating domain, right, which is typically problematic. So for this work, we assume smooth activation functions for the neural network. So the obvious first step that you can do is to assume that I'm going to have a finite now set of points where I'm going to train my neural network. And so that's kind of a first approximation here. We try to solve this problem where we sample some points from the set of initial conditions to create a feedback controller, train the neural network on that set, perform falsification with respect to the requirement, collect counterexamples, and repeat the process until we are satisfied. Okay, so that's kind of would be the first approach to do that. Now, as we mentioned earlier, we have non-differentiable interpretation of the predicates. We also have non-differentiable min and max operators here. So what we do, first of all, is to replace the distance with the simplified interpretation that will not give you necessarily robustness, but it gives you kind of a quantitative interpretation of the value that may not have physical meaning. And moreover, we replace the min and max operators with the typical smooth min and max. And this was suggested or proposed by Yas Pand in his PhD thesis when he was working with my former student Usama Abbas and Raul Mangaharam. They had created a version where they were doing some kind of predictive control using smooth semantics. But this is also useful for training neural networks, right? So the challenge, though, with that is that this smooth min and max operator depends on some constant A that may not give you the desired results, right? It will always lower bound the minimum, but for instance, if you are satisfying the requirement, depending on the A value that you select, then this smooth mean might return a value that is actually negative, okay? You can ignore that if your goal is to maximize the robustness or maximize the quantitative interpretation of the requirement, but you can also see that a poor choice of alpha can trap your search in problematic regions. And that's something that our more recent work kind of removes, and I'll present before closing a few results there as well. So how do we train such a system? Now we have created a smooth loss function for our system. And if we try to do blindly backpropagation, then we run into the same problems as in recurrent neural networks. We run into the problem of vanishing gradients. And one way for us to mitigate the impact, it doesn't completely eliminate the vanishing gradients, but mitigates the impact for the class of problems that we're looking at, was to use Lagrange multipliers. So here is our new version of the problem, where we use the smooth min and max and the approximate robustness, smooth now robustness function. And we can formulate a version of the problem where we take the objective function with using co-states. And if you do some math here, now you can compute a gradient descent vector for the weights of the neural network. The details are in the paper. I'm not going to present that here. And now you can compute directions for descent. You need to initialize the weights so that then you can utilize the descent. And of course, here again, you'll be doing this loop where you detect falsification counterexamples and then retrain the neural network. And here's an example on a quadrotor mission where this is the system dynamics. The specification is to reach a goal set while avoiding the unsafe set. This is just a toy problem to show how this works. You start by doing sampling using CMAES algorithm, which is kind of a typical algorithm for the setup. You get trajectories that may not satisfy the requirement, but after you apply the Lagrange method, they converge all of the trajectories to satisfy the requirement. But of course, here we are not done, right? What is missing here, we have done our analysis over a finite set of samples, but we would like to show that the feedback controller works for any initial condition that you may have in your set of initial conditions. So now this brings me to our recent work, where we are trying to verify neural networks against temporal logic requirements. And this is work presented at ICCPS and HCC last year. So what is the setup? We have the same system, we have the requirement, we have a set of initial conditions, and we would like to show that our neural network trained over these weights W will satisfy the requirement phi for any point that you start in a set of initial conditions. We have a requirement that can be complex, such as eventually P1 and eventually P2 or eventually P3. You can imagine that you can sample trajectories, you can test, and you see that you're satisfying some of the, satisfying the requirement. But ideally, you would like to do it for the whole reachable set, right? To have some proof that the system is correct. So how do we do that? An alternative way, just saying, okay, the system is correct or not, would be to find the robustness value as given in our interpretation for any point in the set of initial conditions, right? So you have the set of initial conditions, you propagate it through the neural network, and you get as an output the range of robustness values. And if your minimum is not below 0, you are guaranteed to be correct. And also, as a side benefit, you get here the robustness value. So Navid, who is a PhD student of Georgios from USC, was working with us a couple of years back in summer as a research resident, and came up with this cool idea where he replaced conjunction and disjunction with ReLU networks. So I really like this idea. So you can represent minimum as a combination of ReLU networks and maximum as a combination of ReLU networks. In the beginning, it might look a little bit complex, but if you read the paper and you can easily confirm to yourself that this is a true relation if you do a case-by-case analysis. So you get the following interesting result, that the robustness is positive if and only if a network created by composing these ReLU activation layers is giving you as an output greater than 0 value, which means, of course, that your temporal logic task is satisfied. So what do we do then? Here's an example. You have this requirement, simple requirement, always x has to be greater than 0, or eventually within one time unit, y has to be greater than 3. If you expand this formula to compute the satisfaction, you're going to get an OR here for this operator, or for this eventually operator. And you have to shift the time. It is OR in the beginning of time, times 0, or at 1, or at 2, or at 3. And then you take an end for the always operator, and that gives you the truth value for this requirement. And you can translate this to min and max. And of course, you can replace this with ReLU networks, and then you can imagine that this now becomes a neural network that computes exactly the robustness estimate or the robustness degree. And now what you can do is you can unroll your dynamical system and the controller. So you have here at time 0, dynamical system and controller. You get the initial state, you output the control action, you take F, and you compose a number of them. You get the values of the state after applying the controller for your finite horizon of the temporal logic requirement. And you now compose that, forward that to the neural network that computes the robustness degree of your requirement. And what's happening here is you're having now a big neural network that returns the robustness with which you satisfy the requirement for a specific initial condition. And what is the benefit of that? You can use any existing neural network verification tool to give a set of initial conditions, propagate it through the neural network that you have generated, and get the range of the robustness values, mean and max values. In this exercise, in this paper, we used NNV, which can provide exact reachability analysis and approximate reachability analysis. But you can apply this to any reachability analysis tool. And actually, in the paper, we have also an approach that using Lipschitz constant that can compute the reachable set. But for this example, we are using NNV. We utilize, for this example, we used an adaptive cruise control system taken from the Sherlock repository, which is another library for reachability analysis of neural networks. This is the system. It is approximated by a neural network so that we can use the NNV tool. And if you want to do exact reachability analysis for this requirement that we discussed, if you violate the safe distance, then within some time, you're going to be satisfying again the safe distance. If you do exact reachability analysis, it's time consuming, but you compute a robustness range. If you do approximate reachability analysis, it's much faster, but you can see here that the robustness range that we can compute is much wider than the exact values, right? So you can see that you can get the lower bound is a lower bound of the exact minimum robustness value, and the upper bound in the approximate case is an upper value of the exact upper bound of the robustness value. But since these values are above 0, we know that the system, the neural network, will satisfy the requirement. All right, so that kind of concludes that part. I have a slide here for scalability. We did some numerical exercises where we increase the complexity of the requirement and we report the times. It shouldn't be of surprise that as you add more depth in your requirements, because the neural network that represents the specification becomes larger, you're going to have to pay more verification time. This is potentially doable. This is okay because this is an offline verification. This is not running online. And also, in practice, though, we may not get as deep nested temporal logic requirements because most of the requirements that we care about are kind of the class of requirements that are reactive. If something happens, then I would like a controller that reacts and does something else within so much time. So we have this kind of class of reactive requirements that are typically needed for supporting autonomy. And we think for that type of requirements, then this is all scalable and manageable. All right. Another line of work is trying to verify, again, neural networks, but now our reachability tools should handle probability distributions. For instance, for the example that we're looking at, you may be reading distance, but you may have actually probability distribution over which you would like to verify the system performance, right? So for that, we are collaborating with Tran from UNL, and we are developing neural network verification tools that can handle such uncertainty over the set of initial conditions. Here we have an example of Tran's work where they're using this on F110 systems. They take some measurements and they compute the uncertainty over the distance estimates through neural networks, and they propagate that uncertainty. You can see here the reachable sets that actually give you also the probability over which it is expected that the system will be in that state. So the main theme here is that you have a probability distribution as an input. Here we assume that this is a multivariate Gaussian distribution as an input that is also truncated. We have bounds over the set, and this is propagated through the neural network. And at the end, we would like to find out what will be the probability that the output of the neural network intersects the unsafe set or some property P. And if it does, with how much probability. For this line of work, we are kind of restricted to ReLU activation functions, but you can imagine we are working towards other, supporting other activation functions as well. The main key of the theory here, and I'm now realizing that I might be running out of time, but let me at least give you a little bit of the background. If we have a representation where we assume that the state is following some Gaussian distribution, then we can form what we call probabilistic star representation, where we have the variable with the distribution, the normal distribution, plus the important part here is number of predicate constraints. These predicate constraints might be coming from the set of initial conditions, but also they are coming from the ReLU activation functions and potentially through the set that the safe set we are trying to intersect with or check safety against. So the interesting thing here is that any affine mapping of a prop star results in a prop star. You can do an affine transformation over your Gaussian. And we do propagation layer by layer. And you can imagine now that when you have a set, and here this is a two-dimensional, let's say, set propagated through the neural network, when we check an activation function, a ReLU activation function, we'll have to find the positive range for the activation function and the negative range, right? So these type of constraints now start collecting in the prop star representation, and the prop star representation starts growing in terms of the predicates that we need to consider, but then we get a description of the exact set that will result if you go through the neural network. So in order to do that, we'll have to allow for intersection with half spaces. Prop stars also naturally support adding further constraints in the representation and remaining a prop star representation. And the challenge here becomes, how do you sample such a space, right? So at the end of the day, you have a Gaussian distribution, and you have a bunch of constraints that you would like to sample from to find out the probability that the state of the system is going to be in that range of your state space. This is you can use potentially existing techniques, such as MATLAB, built-in MATLAB functions. But these existing techniques were primarily working when the number of constraints were less really than the dimensionality of your random variable, which is clearly not our case, because we keep going through the neural network, we collect a lot of constraints that we have to take into account. And we have proposed a way to sample by decomposing using singular value decomposition and approximating singular values using Dirac functions. And we can now sample this type of distributions and give you a probability for that. So as a very simple case here, let's assume we have this very simple 2 input, 2 output, 1 layer neural network. You have this input distribution. So we have these sets for input. And what you get here is such an output representation where you get these partitions of your state space. And what you see here is the probability that the output will be within this set. Okay? So we have now this kind of representation. And if you have an unsafe set, you can take an intersection with the unsafe set and compute what will be the probability that the unsafe set will be reached and therefore the property will be violated. All right, so this kind of concludes the verification, the recent results of, on verification. I could stop here and go to the conclusions if we really want to keep it on 1 hour. Otherwise, I can take any questions about the verification and move on to saying how our recent results on neural network training, which is a couple of slides only, and describe how we have scaled up neural network synthesis. Any preference? Do we want to keep it 1 hour exactly, or we have a few more?
If you have a couple minutes to give us an overview, I think many of us will be at the EDHS, but
okay, great.
You can give us that, and then we have a few questions.
All right. I guess then you can go and ask Navid the questions. We will continue working with Navid, and this is a paper presented, he will be presenting at DHS. So if you recall, our original approximation of the robustness, temporal logic robustness, was using soft min and max, which can be problematic, right? Especially if you view this in the context of verification that I mentioned here, right? Okay, now I'm going back too much. Like when we get a range here, we would like to know what's happening with the lower bound, right? So let's move back. Navid has been playing with all kinds of approximations, and he came up with this new approximation using soft plus Swiss neural network approximations for min and max operators, which has the following interesting property. If the temporal logic value that you compute using this now different version of min and max, which are still smooth, you have the following property. If you are positive, then you have the guarantee that the robustness is going to be positive. So this gives you better performance over your training algorithms. And Navid is going to go over more details about this. In addition, we were working on how to scale up training for really long trajectories. And for that, we used a concept called critical sampling time for temporal logic robustness satisfaction, which means given a trajectory, when you compute the robustness value, this robustness value corresponds to a specific point in time that gives you a distance to some predicate, which is the critical predicate, what we call critical predicate. That distance, if you perturb it, you have the potential of definitely making the robustness worse. Like if you move towards the set, you are going to make the robustness worse. If you are, or actually if you move away from the set, you have the potential to make the robustness worse. If you are inside the set, if you move that point, you can increase the robustness and so on. So we can take that point and use that as a starting point, and we can undersample points over the trajectory. And now we can do our backpropagation over only some of the inputs, not all of them. So we keep some of the inputs fixed as given by the previous iteration, and you do the backpropagation over only some action. So for example, here we will do, we'll compute the action A0, we'll compute the action A4, A5, and the action A9 or control input A9 for the system, but we'll keep the other values fixed. We don't touch them. And that reduces a lot the backpropagation that we'll have to consider, reduce the impact of vanishing gradients and so on. And just to see how this scales, now we can handle, for example, a system with 10 autonomous cars, design a centralized controller for a complex requirement like this one. All the vehicles should reach some goal within certain time, and all the safe distances need to be preserved. So you write this big requirement, you have this big system, and you can run the system and actually solve it, right? Do I have the animation here? No, I don't have the animation. So we are progressing and we are scaling up, and this is very exciting. I don't think Navid is going to present that, but the results are actually already on archive, and you can check them out. All right, so that's what I would like to present today. Some closing remarks. We kind of are pushing towards temporal logic requirements as constraints for synthesis of neural network controllers. Ideally, you would like the neural networks to use data to learn, potentially through imitation learning or other techniques, something that is closer to the desired behavior, let's say through data, for example, how humans drive in certain scenarios, while also imposing constraints. What we presented here was trying to, of course, use robustness as a guide, as a cost function for training the neural network. But ideally, we'd like to move towards incorporating naturalistic data in these training techniques. What we have presented so far shows that feed-forward neural network controllers for reactive requirements and longer horizon tasks is now possible, even for kind of larger scale dynamical systems. Some of the current problems that we are looking at is scaling to even longer horizon tasks, maybe with bigger architectures, let's say, doing deeper architectures, transformers, things like that. Can we do that? Neural network repair after failed verification. So if you do reachability analysis, for example, as it is in here, and you detect a region that is violating your requirement, you would like to propagate that back to the set of initial conditions and identify these unsafe regions and repair them automatically. We have some work along these lines, but this is clearly a problem that is still open and it's challenging as well. Repair after verification. We would like to also think about recurrent neural network synthesis, because right now we do feed-forward. A lot of the challenges we have solved for feed-forward now apply to recurrent neural networks. But ideally, we would like to have a more general framework here. Not so much in terms of theory, but in terms of practical tools for synthesizing recurrent neural networks. And of course, are any of these tools relevant to anything beyond neural network cyber-physical systems type of classes? Now, as a final comment here, given that this is also kind of potentially inspiring collaborations for the future, what are our priorities in terms of safe AI? This is the research that we are doing in our group. We would like to do performance verification, especially for generative AI systems. Even theoretical questions. Is it possible to prove correctness for certain classes of generative AI systems, especially the ones that are integrated with cyber-physical systems? Trustworthiness. How do we know that the AI-enabled systems are aligning with the user goals? How we can do integrated symbolic human-like reasoning? This falls, of course, the work I present today falls along these categories, right? Because we are incorporating temporal logics within neural networks for both verification and synthesis. So this falls under the general theme of neurosymbolic computing, but we are looking also for other possibilities. Another is embodiment. How do we incorporate neuromorphic devices within robotic applications or neuromorphic architecture so that we are energy efficient, memory efficient, and so on? And of course, the bonus problem that kind of bugs us these days is CPS design exploration through AI methods. This is the list of references for the talks, for the works I presented today. I would like to thank all the collaborators, and these are the tools that we have available covering some of the works I presented here. Some are not released yet, especially in Navid's work, but this is hopefully going to be the case before he graduates. He will have to also release some tools. And I'll stop here. Thank you for your attention, and I'll be happy to take any questions you have now.
Thank you for the great question, great talk, and the great questions at the end. I think those are great future directions. I see a lot of overlap with things that we're doing here, but I know you have a short timeline, right? You have maybe a few minutes?
Yeah, maybe 5 minutes. Yeah, I can stay.
Okay. All right, I wanted to offer everyone an opportunity to ask a question. Okay, so I couldn't help from not asking the question. You had a slide where you're looking for the weights, right? So I took a picture of that. So that's the slide 21, right? So closed loop system with FNN controller. And we're working on a very similar problem. And I guess it's not a trick question, but have you been able to classify family of systems for which that problem has a solution?
Wait, didn't go to 21. Give me a second.
Yeah, no problem.
Can you still see my screen?
We see your back there, I think, but okay, now we see you.
All right. So what was your question here? Like this class of systems?
Yeah, have you been able to somewhat write mathematically a proof of, okay, for systems on this class, one will be able to find this controller that will guarantee the desired property?
So you want, the idea here is that you would like to satisfy that for any initial condition, type of feedback controller given any initial condition, or for a single initial point?
It doesn't matter to me too much. I mean, I imagine that the X0 will be something that either is imposed or either is a result for where the controller works, right? Typical basin of action slash region of operation. But even if that's not an issue, even if you're okay with a very small region X0, have you been able to say something about the existence of this controller?
No, we didn't look the existence problem. And here by existence, you mean a neural network controller that would guarantee, right, no matter what the initial point in the basin of attraction that you would like to formulate. Because at the end of the day, you're saying, I'm going to design that, right?
Right.
And so are you asking, do you have enough layers? Do you have enough neurons? Because we know that you can come up with a ReLU architecture that can approximate any function that you would like, given sufficient number of layers, neurons, actually just even a single layer, given a sufficient number of neurons. So I would pose that as a different question. What is the classes of functions for which anyway you can prove existence of such a system? And therefore you know that the existence results exist where it says you can find an approximate neural network that would approximate that function, right?
Right, but the approximate is not the same as the actual, and that's a problem. That's kind of the sticky point, right?
Right. It is, but then I guess you can, you know that better, but I guess you could move also some kind of robustness.
Right, exactly. That's what I was alluding to, exactly.
Yeah.
So there has to be some sort of a robust stabilization result that will give you the hope that then this would work.
Right, right.
I haven't seen it written down, so I was wondering if you...
No, I don't think I've seen this written down as you said, but there's so much work that, you know, it's maybe easy to miss it. Yeah.
Yeah, it's usually a stability result for neural network controllers. And then, you know, certainly that F is nonlinear, then that class is probably rather, I wouldn't say too narrow, but it's generally bounded, right? And it would be you would need to be cautious in situations where you have obstacles, where you have a partition of the state space, like
Right.
so that right. Okay.
Yeah. And just to give you one potential issue here, for this line of work, we didn't particularly address the issue of having to go through the same part of the state space, right, to satisfy your requirement. Because there could be class of controllers where they will require you to go back to where you have been through to satisfy a complex requirement. And for that, you would need some kind of architecture with memory in terms of the neural networks. And that's why you would need recurrent neural networks. We didn't address it in this work. For this type of systems, since we are planning to have a set of initial conditions, you could, and bounded time, whatever requirement we state, it has to be satisfied within bounded time. You can typically add time also as part of your state, right? And therefore you can design time-based controllers that can potentially resolve the issues of memory. But more generally speaking, I suspect to address the problems that you're mentioning, you would need some kind of recurrent neural network architecture.
Yeah. That would be an interesting discussion.
Yeah, and I would love to follow up, and maybe we can have another discussion at some point.
I'm taking note of that on the picture. Thank you.
Yeah, thank you for listening.
Any other question quickly? Otherwise, we will.
Yeah, I think it's time for me to go anyway.
You need to go. Okay.
Yeah. Bye-bye.
Thank you so much. Appreciate it.
Yeah, bye.